Hello, dear students. I am here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Dear students, in last video, we have seen the generalized instrumentation system along with its characteristics and some performance parameters. So just review the last video and then we will go next part of the instrumentation system. This is third video on the instrumentation system. This instrument characteristics we have seen, transducers, and these characteristics we have seen. What is transducer? Use of transducers, classification of transducers, and certain transducers, resistive, piezoelectric, LVDT, etc., thermistors, strain gauge, types of transducer, transducer performance characteristics, input, output and transfer characteristics, certain questions which I have given to you, then generalized performance of a instrumentation system, definition of the instrument and philosophy of the instrumentation, its history of the instrumentation. Then we have also seen the measurement, and this is the block diagram which we have seen, generalized block diagram of the instrumentation system, primary sensing element and secondary transducers, data transmission element and data presentation element, static terms and characteristics which we have seen in the last video, like accuracy, sensitivity, static sensitivity. Then this is linear and non-linear characteristics of the instrument along with the static sensitivities, overall system sensitivity. If certain systems are cascaded, then we can calculate the overall system sensitivity, that is K theta 1 by theta I into theta 2 by theta I into theta naught by theta 2, that is K is equal to K1 into KT3. Then static error, then accuracy, precision, reproducibility, drift and repeatability. These parameters we have seen. Later on we have gone through the stability, resolution, linearity, and then I asked you the questions. Write a note on repeatability and reproducibility are synonymous. Compare between sensitivity and drift and certain problems. Then dynamic terms and characteristics. It is used to measure time varying process variable. Characteristics gives the relation between the instrument's input and output. Dynamic performance is represented by following terms. Dynamic performance is given by speed of response. It is defined as the rapidity with which an instrument responds to a change in the value of the quantity being measured. This is the speed of response. Then lag, measuring lag. It refers to delay in the response of an instrument to a change in the input signal. So if we change the input signal and there is a delay in the output, it's called as measuring lag. Fidelity. It is the ability of the system to produce the output in the same form as the input. It's called as fidelity. We know that we write hi-fi. High fidelity. Hi-fi means high fidelity. So that fidelity, it is the ability of the system to produce the output in the same form as the input is called as fidelity. For example, input is sine wave, then the output becomes the sine wave. Only that means 100% fidelity is obtained. Then dynamic error, static error we have seen. This is dynamic error. The difference between the indicated quantity and the true value of the time varying quantity is the dynamic error. Overshoot. It is defined as the maximum amount by which moving system moves beyond the steady state position. It's called as the overshoot. Dead time. It is a time required to instrument to begin to respond to the change in the measured quantity. Try to understand the definition, read it properly and understand this overshoot at dead time. Dead zone. It is defined as the largest change of the measurand to which the instrument does not respond. Whatever is the measurand change is there, in which if the instrument does not respond, the zone is called as the dead zone. Then standard test inputs. For testing the input and circuit, we use some standard test signals. These standard test signals are the test inputs. And the most commonly used standard test signals are like a step function, ramp function, is also called as the linear function, sinusoidal or sine wave function. Then parabolic function is also used. Here is the definition of the unit step signal. This is in terms of the discrete signal. U of n is equal to 1 for n greater than 0 and u of n is equal to 0 for n less than 0. So this shows here the step signal. And this is the sampled value at t is equal to 1, n is equal to 0, 1, 2, 3, 4, 5. Here you will get this value equal to 1. And here this value is equal to 0. So this is like a step. This is a standard function used for testing. Ramp or linear function. This is a ramp type function. You can see here. And this ramp function is given by R of n is equal to A into n, where A is the amplitude, or you can write n simply. R x of t is equal to A into t is the ramp, where A is the amplitude and t is the time. Similarly, R of n is equal to n. N is the time index in discrete time. This is called as a ramp or linear function. This changes linearly with respect to time. This is time and this is amplitude. This may be a ramp. Ramp may be a positive or negative. In the input varies with time. In it, the input varies with time. The ramp input is mathematically expressed as, here it is written theta I is the ramp input is equal to k at t greater than 0 and theta I is equal to 0 at t less than 0. As per this diagram, theta I, let us say supposed to be vertical axis is theta I and this is t. So theta I is greater than 0 is increasing and less than 0 it is 0. Where k is the slope of the input versus time relationship. Then another input signal is the sinusoidal sequence. You can see this is discrete sinusoidal samples are shown here. X of n is the sinusoidal signal. If it is not discrete, you can continuously draw this, join this. And this n will change to t. This is time domain. And this x of n and n is the discrete time domain. So this diagram shows the discrete time domain sinusoidal signal. Otherwise you can write here x of t, t and continue this one. You will get the time domain. This sinusoidal signal is given by x of n is equal to a cos n omega 0 plus phi. Phi is the difference and a cos n omega 0 is the sequence. Here it has a cyclic relation. The input varies sinusoidally with a constant maximum amplitude. Mathematically it is represented by theta I is equal to a sin omega t, where a is amplitude and omega is the frequency in radian per second. This is sinusoidal equation. Then 0th order, first order and second order system. A system whose output is directly proportional to input. The output is faithful reproduction of the input without or any distortions time lag. This is given by theta naught is equal to k into theta I, where k is sensitivity, theta I is input, theta naught is the output. And this equation is called as the 0th order equation. Above equation is 0th order system, which is obtained when the power of n is set to 0 in the general equation for a measurement system. So a naught into theta naught is equal to b naught into theta I. So theta naught is equal to b naught upon a naught into theta I is the first order system. The behavior of the first order system is represented by a first order differential equation of the form a1 into d theta I by dt plus a naught into theta naught is equal to b naught into theta I. Or in terms of Laplace variable, the power of s should be equal to 1 for the first order system. If we substitute n is equal to 1, then write tau is equal to a1 upon a naught and k is sensitivity, k is equal to b naught upon a naught. This is the first order system. You can see, if this is a second order, then differential equation becomes a second order equation. Our Laplace variable can be s square. For example, temperature measurement. Temperature measured by mercury in a glass thermometer, thermocouple and thermistor is an example of these systems, first order system. Now it is a second order system. The input and output relationship of second order system is described by a differential equation of the form like a2 d2 theta by dt square plus a1 d theta by dt plus a naught theta is equal to b naught theta I. Theta I is the input and theta naught is the output. Above, this equation is obtained by n is equal to 2 in general form. This is second order. Differential equation is of second order. And in terms of transfer function, Laplace variable is also of a second order, s square. Then the system becomes a second order system. Like the polynomial, we use ax square plus bx plus c is equal to 0 is of second order. Similarly, any system having a transfer function with a power of s is equal to 2 gives the second order system. Example of second order system or second order instrument are ultraviolet galvanometer and pain control system on XY plotter. This is second order system. response of a first order control system. This is theta naught upon theta I output upon input is equal to 1 upon tau d plus 1. This is first order, and in terms of Laplace variable you can write 1 upon 1 plus t into s. Since s having a power 1, t is the time constant, is called as a first order system. This is the output C of s, R of s is the input. So C of s upon R of s is the transfer function, which is equal to 1 upon 1 plus Ts. This is the response of the system for the step input, unit step input. For unit step input, the transfer function is C of s upon R of s is equal to 1 upon 1 plus Ts. First order system. This is transfer function. If you take the inverse Laplace transform of this transfer function, then it is given by C of t is equal to, in one bracket, t minus small t minus capital T plus capital T into e to the power minus t by t. And the error signal is given by E of t is equal to R of t minus C of t. R of t is the input, reference input, and C of t is the output. So this error signal can be calculated. An instrumentation system or with instruments, we can calculate the steady state error or static error, ESS. For this equation, this ESS is equal to capital T. Similarly, we can calculate for the second order system. This is the transfer function for the second order system. General C of s upon R of s is equal to omega n square whole upon s square plus 2 zeta omega n s plus omega n square. Omega n is the natural undamped frequency. Zeta is the damping factor. This is the second order control system. And you can solve this second order control system to get the time t or transient response. This is not need to you now, so you can leave this. These are the characteristics of the second order system. Dependent on the roots, three conditions are responsible for determining the transient response of the system. One is called as overdamped system, where zeta, that is damping factor, is greater than 1. Critically damped system, where zeta is equal to 1, that is damping factor is 1. So underdamped, underdamped system is one where damping factor is zeta is less than 1. So these are three possibilities in the second order control systems. This is once again it is given, and I would like to ask the question here. Give the name of any two second order systems. Try to find it and let me know what are the two second order systems having a transfer function with power of s is equal to 2. Then one of the important term in instrumentation system is the calibration. Calibration is the process of quantitative comparison between a known standard and the output of the same measuring system measuring the same quantity. So in general language we can say that whether this instrument is properly calibrated or not. So this is the meaning of calibration. Calibration is a process of quantitative comparison between a known standard and the output of the same measuring system measuring the same quantity is the calibration, or it is also defined as the process for determination by measurement or comparison with the standard of the correct value of each scale reading on a meter, or determination of the setting on a meter of values voltage, current, frequency, pressure, flow or some other output. Performing a calibration of the instrument, the following steps are necessary. While doing calibration, we must have: number 1, examine the construction of the instrument, list all the inputs. Examine the construction of the instrument, list all the inputs. Second, decide one input which is applicable for significant input and for which it is calibrated. Some inputs considered constant, varying. Others record result and get static input and output relation. This is the process of calibration shown here. How we can forward for the calibration? You can go through it. There are primary calibrations, secondary calibration, direct calibration with a known input source, indirect calibration and routine calibration. These are the steps for the calibration procedure: visual inspection, checking the instrument, zero setting of all the indicators, operational test to detect the major defect, leveling of the devices. Calibration of instrument must be in ascending or descending order of the input values. The calibrate device should have superior level of traceability of the standards. So this is regarding the parameters, like calibration. It is not parameter, it is a process to have the better instruments. Then this is a resistive transducer. The resistance of a metal conductor is expressed by a simple equation that involve a few physical quantities, like R is equal to rho into L upon A, where R is the resistance in ohms, L is the length of conductor, A is the cross-sectional area of meter of conductor, that is in meter square, and length is in meter, where rho is the resistivity of a conductor material, ohms meter. So this is all about the general instrumentation system which we have seen. Kindly go through the all 3 videos. Later on we will go for the measurements of some variables, measurement of some quantities like temperature, pressure, physical quantities. We will go to study this measurement. But before that, this general instrumentation system is very important. So I advise you to go through it in detail. And if you have any difficulty or doubts, you can ask me on any platform. Thank you very much for watching this video. Thanks a lot.